All right, I hope you can see my screen and hear me.
Everything good? Thank you.
Let me start by thanking Argia and Oliver and all the organizers behind this webinar for this nice initiative and the opportunity to interact and share our work. So I will also be talking about alkaline electrolysis. Christodoulos Chatzichristodoulou from the Technical University of Denmark, DPU Energy. I will also be talking about alkaline electrolysis, but at a somewhat lower tier level than what you heard just before me. I will not be presenting all activities associated with power tricks in this department, just some examples of activities within my project and my team. So, alkaline electrolysis, there are certainly several challenges. As we heard before, it's perhaps the most established technology and cheap and large scale compatible that we have today, but it still has lower efficiency and lower production rates than other technologies. So there's definitely room for improvement in terms of performance, lowering degradation, expanding dynamic range, and reducing cost further. And of course, reducing cost can benefit a lot from large-scale implementation, as we just heard. But at that point, then the cost of materials becomes very substantial, actually. So utilizing lower-cost materials is also very important. To boost performance, we can make better catalysts, better electrodes. We can intensify operating conditions. Degradation, especially under dynamic operation, is a challenge, and we need to test more and collect more data under industrial conditions. We also need to establish relevant stressors and develop accelerated stress test protocols and lifetime protocols in order to speed our understanding of degradation processes and our ability to study them. We need to understand crossover and try to minimize crossover, which is one of the limiting factors for dynamic operation in alkaline electrolysis. Yeah, as already said, avoid use of PGM materials, which is actually still used in some of the high-performing alkaline electrolyzers today. So, how can academia contribute to that? For the time being, there is a lot of work carried out in academia on new exciting catalyst materials, but unfortunately, most of the work is carried out at low temperatures, low current densities, dilute electrolyte solutions, so far away from the conditions of operation in industrial alkaline electrodes. And this, I think, is something we need to seriously take into consideration, because if we want to develop materials that are of relevance for the industry. So at DPU Energy, we actually try to test and develop materials at industrial conditions and beyond. This is possible both with rotating disk electrodes that are commonly used for fundamental studies of catalysts, but also with small electrodes and other components. It's possible to heat up the RDE and use concentrated electrolyte solutions. We at DPU have also developed custom-based pressurized containers where we can do electrochemistry with free electrode holders to accommodate different types of components and samples, actually. So we can cover temperatures up to 250 Celsius and pressures of at least 50 bar. We also try to accelerate catalyst development, and we try to do that by both automating experimentation and establishing high throughput collection of data, as well as combining that with active machine learning algorithms in order to speed up the experimental approach to the optimums we are exploring at each instance. So the idea here is that we have a robot basically synthesizing a catalyst and then transferring that to a system where testing takes place. Then there's automatic analysis of the data and development of a database that is then analyzed by active machine learning algorithms that can then guide the selection of the next experiment to speed up the identification and discovery of better catalysts. Advantages are obvious here. You can have 24/7 operation, optimized use of resources, improve consistency of the measurements and the data collected, and we can elevate the role of human resources to the more creative part of the process rather than the tedious synthesis and testing that has a lot of repetition and it's very time consuming. So with so our approach in that respect was inspired actually by the roll-to-roll approach in manufacturing, because this provides for a simple and robust transfer of the sample between different stages required in the synthesis and testing process. It also allows for the different stations to be customizable, and it allows for a lot of flexibility. So what we have in this case is basically a substrate that is transferred by being rolled around between some cleaning and prepping stations, followed by a synthesis station where the catalyst is being synthesized and coated on the substrate, and finally a testing station where electrochemical testing takes place. This is how our system we have built looks like. We have a set of stock solutions, each coupled with a syringe pump that can then very accurately dose and mix a number of these stock solutions and supply them to the synthesis or testing or prepping stages. This is the roll-to-roll system here, guided by a stepper motor that pulls the substrate, which for the case of alkaline electrolysis was just a nickel wire. And then it's transferred, it's passing through an acid bath where this is being cleaned and then cleaned with water before it goes into an electrodeposition stage where different components are mixed. So we can have different precursors at different ratios. The temperature can be controlled, the current density of the deposition or the overall profile of the deposition can be controlled. Finally, once this is completed, the chamber and the electrode is washed with water and transferred to the pre-electrode testing cell where electrochemical testing takes place at industrially relevant conditions. Again, we can control the concentration of the electrolyte and we can control the temperature up to at least 80 degrees Celsius. So all the data are then analyzed automatically and fed into a machine learning algorithm that further guides the next experiment. This is how it looks in real life. This is the liquid distribution system, the potentiometer here, and this is the roll-to-roll testing station with the different stages and the collecting drum where the synthesized or tested catalyst is collected and can be traced back if further characterization is required at the end of the experiment. We have performed very diligent qualification of the platform. Here you see, as an example, the nickel hydroxide to nickel oxyhydroxide transition, both at 30 degrees Celsius, half a molar KO8, where academic literature exists and we can compare with, but also at 80 degrees Celsius and 6.9 molar KO8. Indeed, we find that here you see 4 repetitions at each conditions. You see there is excellent reproducibility, excellent precision, with very little standard deviation of the peak position in each case, but also excellent accuracy with the peak position actually being where it would be expected in an electrolyte with trace levels of iron impurity. And the transition towards lower potentials with increasing temperature and increasing intensity of the peak. We have also qualified the platform by measuring hydrogen evolution reaction on a nickel wire substrate. You see again 4 samples here, 4 repetitions at 50 degrees Celsius, 6 molar KO8. This is chronopotentiometry measurements, the ever potential at 1 to 50 milliamp per square centimeter. you see there is a standard deviation of the order of 3 millivolts at an overpotential of 400 millivolts, so extremely accurate measurements. Then the protocol we used included an accelerated stress test protocol, including 100 CV cycles, going from negative cathodic potentials up to 0.7 volt. And again, we saw a quite complex profile of the overpotential at cathodic conditions of -5 milliamp per square centimeter after each one of these 100 cycles. At the beginning, we see an activation of the HCR response, followed by a deactivation. We have a working hypothesis of what is the physical processes behind this profile here. But what is important to stress here is actually the reproducibility of this complex behavior in different measurements. And then again, doing hydrogen evolution reaction from the geometry measurements after the AST protocol, again, we see very reproducible performance. Finally, we investigated the reproducibility of the platform when we do electrodeposition of nickel on a nickel wire. And again, although the standard deviation is slightly larger than that of a nickel wire and slightly somewhat dependent on the actual deposition conditions, here we have 5 repetitions for 3 different sets of deposition conditions listed here. In all cases, the standard deviation is quite small and more than adequate to employ the platform for optimization processes with electrodeposition. So being convinced that the platform is functional, we attempted the first experiment where we tried to do optimization of nickel molybdenum alloy catalytic coatings for hydrogen evolution in alkaline environment. This is a list of the parameters that were included in the optimization and the ranges employed. So that was the amount of nickel and the molybdenum precursors in the electrodeposition solution, the pH of the solution, the deposition current time, and deposition temperature. And the way we qualified the performance of the electrode was again by doing 100 CV cycles between cathodic potentials and 0.4 volt anodic potential at 50 millivolts per second, and then analyzing the results with respect to the overpotential at -10 milliamp per square centimeter over these 100 cycles, and taking the total integrated area below this overpotential. Basically, the average overpotential over these 100 cycles as a combined metrics for both the activity of the coating and the stability of the coating under cycling in this potential one. Here's the evolution of the combined advantageous score of each coating as a function of experiment. We carried out 150 experiments, which required less than 3 weeks' time to be completed. Here you see the ability of the algorithm used to predict the actual experimental values measured. With an R-square of 0.66, fairly good predictive ability. The color that you see here indicates whether the model was employing a more exploratory approach or exploiting the already collected data. And we employed a mix of exploration and exploitation of the results in order to identify the optimum in this synthetic phase space. And by doing so, within 150 experiments, we managed to get very active coatings that required less than 180 millivolts over potential at 10 milliamp per square centimeter surface area normalized activity. That showed no activity loss over these 100 CV cycles. Now, besides coatings, it's also very important to develop electrode architectures in order to get good electrode performance. And here, mass transport and ease of removal of bubbles is very important. And we try to approach that by combining detailed electrochemical testing with multiphysics simulations and the characterization of the fabricated electrodes. With respect to the detailed electrochemical testing, we have developed a novel method to carry out, to analyze the electrochemical response of a cell at zero cell configuration, zero gap configuration. Here you see the diaphragm and the two electrodes. We're placing a reference electrode right in the middle of the reference of the diaphragm, as well as two reference electrodes behind each electrode. And this allows us to actually separate the contributions from the anode and the cathode, as well as measure how much losses one has within each electrode for transport of ions through the depth of the electrode, actually. So this allows us to understand better how each electrode architecture influences actually the electrode performance.
And as we try to wrap up now in shortly. Thank you.
So we can also use this methodology in order to understand actually degradation of each electrode during dynamic operation or intermittent operation. Here you see the evolution of the cathode overpotential and the anode overpotential over time during dynamic operation. We also try to accelerate electrode development and understanding of degradation through parallelizing testing with 3 electrode holders that can be run in parallel. So with relatively low cost, we can have at least 12 cells running in parallel for long periods of time. So we also, as a final word, we try to intensify operating conditions because by employing autoclaves, custom-made autoclaves, where we can carry out electrochemistry at high temperatures and pressures. This is an example of electrodes tested up to 150 degrees Celsius at 50 bar. And we have also developed systems where we can test full cells under flow at these elevated pressures and temperatures, and measure also gas crossover during operation. So thank you for that. I hope you got a representative picture of what we're doing at EDU, and looking forward to the panel discussion later.
Thank you, Christos. I see we have a question now on improvement of overpotential for NI and NIMO-based catalyst. I propose, because you are slightly over time, we're running about 10-15 minutes late, that we actually take a 6 to 7 minutes break, and we get back to this question in the panel discussion, and we'll touch upon the material aspect at that time. So let's rejoin have a few minutes break and rejoin at 7 minutes from now, which is 10:25 Danish time and 55 in India time.